Welcome back to part two. A Foucault pendulum. It's French. It's a weird spelling. I'll grant you that. This is the Earth Sciences building at ASU, and this is an example of a Foucault pendulum. It's a really heavy mass. I forget. It's like 200 and something pounds in the case of ASU, and I believe this is a picture of the ASU one. It is hung from a fairly friction-free pivot point way high. This has to be very long. You can't do this in your living room. Now, imagine a big dome built on the north pole of the Earth, and from the very top of the dome, what we call the zenith, the highest point in the dome, let's say you had a bowl over you and you had an anti-gravity marble, the place the marble would go if it was anti-gravity, that's called the zenith. Now, if you hung that really big weight on a frictionless pivot point from the zenith, pulled this back and let it go, it would swing back and forth in a straight line. As long as there are no friction or air messing with it, it would go back and forth in a straight line. The curious thing is, it appears to be moving, well, it starts to swing this way, then this way, then this way, then this way, then this way. Why is that happening? This is changing direction. What's happening is the Earth is turning under it. The Foucault pendulum shows that Earth really is rotating underneath us. Now, as you move the Foucault pendulum down toward the equator, you get a diminishing effect. But again, since the Earth is spinning this way, the Foucault pendulum seems to be moving back this direction. I love the little reflections on here. You can see the people taking the picture while leaning over the rail. Again, you get this kind of motion or rotation in the North Pole, so the Foucault pendulum seems to move backwards, just the opposite in the South Pole. But in both cases, the sun seems to rise in the east and to set in the west. One rotation gives us a day. Now, a day typically we think of as 24 hours. Here's the sun, here's the Earth. When it spins around one time, it also is moving around the sun. So this is kind of tricky. To spin around 360 degrees takes only 23 hours and about 56 minutes and 54 seconds or something like that. To spin around so that we're back in line with the sun again takes 24 hours. So there are two kinds of day. Are you talking about the day when we spin 360 degrees or the day when we get back in line with the sun, which is about 361 degrees? Usually we talk about the solar day, 361 degrees, or 24 hours. This is a kind of cool thing. If you shot a gun and somehow the bullet could stay in the air all the way to the equator, and you intended to hit something down here, again, this is impossible, but just work with me here. It wouldn't happen. Why? Because the Earth is rotating under you. While the bullet was traveling, the Earth would rotate underneath it. You'd hit something way behind. It's almost like a football player, let's say Joe Flacco, hitting his receiver where he's going to be, not where he is. The Coriolis effect causes the spinning of the Earth's winds to the right in the northern hemisphere or to the left in the southern hemisphere. So winds and ocean currents are deflected because of this Coriolis effect. Here we go. Anything in the northern hemisphere turns to the right, anything in the southern hemisphere tends to turn to the left, and these winds then end up affecting ocean currents. Now, the speed of rotation, no matter where you are on Earth, it's going to take 24 hours to get around one solar day. But the speed isn't the same all over. If you stand on the North Pole, you're really going no distance around the Earth. You're just spinning in a circle. If your coach told you to take a lap around the track and he had a point in the middle of the track, technically you could just run around that little point. You wouldn't go very far and he'd probably make you do a lot more laps. If you want to really impress the coach, go to the equator and start running around, because you will have to go about 24,000 miles or 40,000 kilometers to go around. How fast are you moving at the equator? Well, you're moving about 1690 kilometers an hour. Up in Boston, you're moving only 1390 or 1300 kilometers an hour. You've got a problem with that? Now, Earth is not straight up and down. It is tilted in relation to the sun about 23.5 degrees. Somebody came along once and tipped us over and never put us back. That's the way it goes. That causes something kind of cool. Here's the direction to the sun, and this is called the ecliptic. However, all the zodiacal constellations like Leo, Aries, Scorpio, they tend to be over our equator, and our equator is not in line with the equator of the sun. Be nice if it were. Kind of bugs me that it's not. We should straighten it out, but that's not going to happen. We have an obliquity of 23.5 degrees. Because of that, some weird things happen. If the Earth were straight up and down, every part of the Earth would get 12 hours of daylight and 12 hours of night every night. But that's not what happens. Earth stays tilted 23.5 degrees, imagine the sun in here, as it goes around the sun in 1 year. That means when we have our maximum tilt toward the sun, a point 23.5 degrees away from the North Pole is completely in daylight for 24 hours. So all the polar bears have their sunglasses on. But on that same day, all the penguins are snuggled in bed trying to stay warm because they never even see the sun on that day. If you're north of the equator, take a look. We get this much sunlight. Anywhere from 24 hours of sunlight down to 12. If you're south of the equator on this day, it'll be the summer solstice, June 21st, 22nd. If you're south of the equator, you're going to get less. Now, as the Earth revolves around the sun, keeping the same tilt toward Polaris, the North Star, we end up with the sun hitting what was once the backside of the Earth, but now the Antarctic Circle marks the line of maximum solar extent, and the line inside of which you would see 24 hours of sunlight if you're a penguin. The polar bears? Cold, drinking their Coke from their ads on Super Bowl. No, that's Christmas Day, isn't it? Whenever those are on. Now notice the equator always gets 12 hours of daylight and 12 hours of sunlight. They're kind of equal, which might give us the name equator. The line 23.5 degrees north of the equator is called the Tropic of Cancer, because in America we eat all kinds of weird food and we get cancer. They have lots of goats in the southern hemisphere, and those of you into the zodiac know that Capricorn is a goat. So remember, the Tropic of Capricorn is south of the equator. This would be good stuff to ask on a quiz. Now, again, a long time ago, people knew that the sun wasn't overhead at the same time in all places. In fact, 360 degrees around the Earth and 24 hours, an hour being an arbitrary unit, it works out that we have 24 time zones. 24 time zones and 360 degrees means that each time zone is about 15 degrees. We call everything in this time zone the same time. Is it really? No. There's an example question in your study sheet. If we all use sundials to establish local time and see when the sun is directly overhead and try and have a meeting at the same time, that's not a good idea. Let's see, United States, 4 a.m. here, 7 a.m. over here in the New York area. We have to agree on some kind of standard. Now, I guess I should go back. We have to start the day somewhere. So in order to do that, we establish what's called the international date line. And a day, by definition, starts here. If you're starting, let's say, February 5th, February 5th starts there at midnight, 1 a.m., 2 a.m., you get the idea, and moves across here until it gets all the way around the world and then comes back here, and the day finishes right here. It should be a straight line, but it's not, because you don't want to split Russia, and you don't want to get the Aleutian Islands into a different day either. So they made the international time zone wiggle a little bit. American Samoa right down here broadcast in 2 different days. WVUV with WK Diamond, my old radio station. This is what Earth looks like from space. And this was, I think, yesterday I took this picture. So this would have been on February 4th, 2000. Notice the sun is hitting the entire Antarctica. And there's a lot of the Arctic that's never getting hit by the sun because right now the North Pole is slightly tilted away from the sun. This isn't bad. This is about the same time. We're in the daylight. The sun is already setting in Africa and it's starting to rise over Russia and the Aleutian Islands. This is kind of cool. If you ever stay awake all night while camping, you will notice that Ursa Major, the Big Bear, and Ursa Minor, the Small Bear, or the Little Dipper, seem to change positions. Here is the North Star. This is the star at which our pole is aimed, and you can find north by looking for this star at night. This is a nice way to stay oriented at night. How many hours did it take to get from this point to this point? There's a 12-hour difference there. You couldn't do this in the summer. You could only see this in the winter when we get more than 12 hours of darkness. By the way, Ursa Minor, Ursa Major is over here. This is kind of cool. Earth also does a weird thing, wiggling like a top. If you go to Wikipedia, this is actually a GIF and it's animated. It shows how a top will wiggle. Well, the Earth does the same thing over a period of many thousands of years. When the Great Pyramid of Cheops or Khufu was built in Egypt, there are these passages that lead out, and they don't lead anywhere right now. It's kind of strange. Scientists couldn't figure out what was going on. Well, a long time ago, the Earth was aimed in a slightly different direction, and those passages used to aim at Thuban, a star in Draco the Dragon. It's called the Alpha Star, the brightest star in Draco the Dragon. Right now, they're aiming at some other point in space because Polaris is our pole star. If you die and come back in about, 6,000 years, our pole star will just be off a little bit from Delta, or sorry, is that Delta or Alpha Cepheus, the brightest star in Cepheus? Just keep that in mind if you reincarnate. This is kind of cool. This isn't really a sundial. There's another name for this, but you're going to get the idea. The sun entering down through this little slit will show right here what time it is. In this case, it says, oh, these guys are crazy, 15, which is 15 hours or 3 p.m. As the sun moves across the sky, this shadow will go over here until 6 p.m. That's one way to tell time. Just buy one of these, strap it to your wrist, and aim this toward the North Star, and you've got a free pocket watch. Or free wrist watch. Okay, maybe it's not that handy. This is also kind of cool. There's a little sun up here with a little hole in the middle, and as the Earth changes its position relative to the sun, this will be where noon is in January, February, March, April, May, June, July, August, September, October, November, and December. This is a noon gnomon. And this is a sundial in Carefree, Arizona, the world's largest sundial. This direction is north, and this was taken a long time ago because there are a lot more houses out here now. Go out and see it. Again, when the sun rises, it'll be over in this direction, so the shadow will be over here. In the evening, the shadow will be over this way. We're going to stop here and pick it up on the other side.